Hi there, welcome to Embedded World 2024. I'm here on the DigiKey stand and I'm pleased once again to be joined by Frederik Dostal, the power specialist at Analog Devices. So thank you once again for joining us.
You're so welcome.
Today we're going to be talking about the intelligent edge and intelligent edge sensors. But before we do that, can you give us a brief introduction to yourself and your background?
Absolutely. So my name is Frederik Dostal. I work at Analog Devices as a power management expert here in Europe. I'm located in Munich in Germany, and what I do is I support our customers when it comes to power management applications on a technical level so that they're successful with our products.
Fantastic. And for those of us who perhaps aren't as familiar with Analog Devices, can you give us a brief sort of introduction and history?
Yes, so Analog Devices, really what we do is we empower our customers with analog, with digital, and with software technology so that they are successful.
Yeah.
That's our purpose in life. So
fantastic. Nice and simple.
Thank you. I memorized it,
Okay, so we all know that the intelligent edge is spreading across industry, replacing heritage edge sensors and actuators. But to start with, what is the intelligent edge? Give us some idea.
That is a very good question. Well, we've had the edge, of course, for a long time. The edge really is the interface between the real world, the analog world, and the digital world that we have nowadays.
Yeah.
So the edge has always been there. And the intelligent edge just means that we empower the electronics at the edge, including software, of course, so that a lot of processes and processing can take place at the edge. So less data has to be transmitted from a sensor or from the edge specifically to a mainframe server or something processing all that information. So the intelligent edge is a step in the direction to put more, let's say, brains to where the sensors are compared to large computing units in the background.
Okay. And give us more of an idea of how the intelligent edge is designed.
Yes. So we are in the middle of the step from the, let's say, heritage edge that we always had to the intelligent edge. And the design has changed a little bit. We still have sensors, of course, at the edge that is taking analog information, real-life information, images, for example, sound, temperatures, or all kinds of things you can measure. But with the intelligent edge, we have some local processing. Let's say, for example, in a building, an elevator would like to know how many people are waiting in front of a certain elevator door.
Okay.
And then with the intelligent edge, the processing would be done locally, image recognition and things like that. And then locally, the sensor would then say, 3 people. And it would transmit the number 3 to the whole building system, so to say. With the non-intelligent edge, it would have just transmitted image data, huge data masses to some certain server, and that server would have to process it. So we're moving the processing in the intelligent edge within the sensor locally so that communications is a lot faster and simpler. But of course, we have to build these intelligent edge sensors.
Yeah.
And when you do the processing then on the edge or at the edge, then you also need enough power to do the processing with.
Yeah.
And this is really where our technology comes in, or my technology as a power management expert, how to make enough power available so that the intelligent edge can actually run, in a useful way. As possible.
Yeah. Can you elaborate more on the use of single pair power over Ethernet and how this is helping to realize the intelligent edge?
Yeah, that's a good question. So there are different sensors, of course, and some sensors are battery powered, other sensors have a power line going to them, but many sensors, especially in industrial applications, are or have been attached with a 4 to 20 milliamp line.
Okay.
So it's typically just a single twisted pair cable going to the sensor. And if you want to make that sensor intelligent now, there's one really nice way with SPOE, with a single pair power over Ethernet.
Yep.
That's what it stands for. Another thing I memorized over the years. Where you can just use legacy 4 to 20 milliamp cabling that's available in many of these installations. And you can transmit up to 52 watts in power on that twisted pair, or up to 1 kilometer of cable length, which is a lot.
Yeah.
Let's say in some refineries or things, things actually need 1 kilometer of cable length. So it's quite interesting. And it's a way of really combining power transmission to the intelligent edge together with base 1T digital communication, sort of like Ethernet protocol type of communication.
Yeah. Can the intelligent edge use common heritage power supplies?
Yes. So in principle, yes, that is possible. But since the edge is more intelligent, it needs a little bit more power to do all the processing.
Yeah.
So that means in some applications, you're constrained by the available power. And if you cannot increase the available power, what you can do is you can, let's say, increase the conversion efficiency so that ultimately you have a little bit more power available on the load side, on the sensor side. Another thing would be, for example, if the power is not enough, you can add energy harvesting to it. And with energy harvesting, you can actually grab more energy that is in the environment, and you can harvest it and add it to that power. So we can already see that it can be quite complicated to work with multiple power sources just to make sure there's enough power available right at the edge.
Okay. So following on from that then, how do new power supply solutions developed for intelligent edge sensors differ from traditional power supply mechanisms?
Right. So I think one of the things is an optimization towards low noise and low EMI. Because if you have a potent or larger power supply close to the edge, yes, you want to power your processing, but you want to avoid that noise or EMI from the larger power supply is actually influencing what you want to measure. Let's say if you want to measure a small signal and there's lots of noise surrounding that signal, it's going to be hard with a large power supply in the vicinity rather than a small one. That's one thing. The other thing really is with the energy harvesting, just that's a power supply that might be more complex if you want to add energy from energy harvesting to an existing battery source or some other power source. So that makes it a little bit more complex too. And then one other thing would be small size. If you put intelligence in the edge, then you also have to make sure that not only the larger processing digital electronics fit within the sensor, but also the necessary power supply. So power supplies also have to become smaller, higher power density in many of these applications. But my answer already tells you it's a very diverse problem to solve. And that's why we need a lot of skills from different power management innovations and areas and fields to really successfully power the intelligent edge.
Definitely. So what specific design considerations then are taken into account when optimizing power supplies for SPOE applications?
Yeah, so I think one design optimization that is specifically needed typically is really the space and the power density. So that means coming up with a PCB board layout where heat can be dissipated nicely. So that's one thing. The other thing is with the EMI. I mean, if we put this larger power supply right at the edge, we have to reduce the EMI, and that's a task for the PCB board designer. So that's one thing people have to focus on. We do help with our products that generate very little EMI, but still PCB board layout is important. And we support our customers also doing this in the best way. And I think this is pretty much where designers have to look at in order to come up with a good intelligent edge design.
Definitely. In the development of ultra low noise power supplies for intelligent edge sensors, then what were the most significant technical hurdles that are encountered, and how were they addressed?
Yes. Okay. Well, so we've got a technology that we introduced about 10 years ago. So it's been around for quite some while, but it has been improved over the years. So now we are at the third generation of our famous silent switcher technology. And the silent switcher technology is the way that switch mode power supplies are built so that magnetic fields that are always being generated are actually split in a symmetrical way so that these magnetic fields are being cancelled for the most part. And this was an innovation which was really enormous about 10 years ago, and still is. This is really the best you can do in switchboard power supplies to get the noise down without sacrificing efficiency drawbacks.
Okay.
So the efficiency is quite extremely high. And I mentioned this. There was a first generation 10 years ago, then there was a second generation with where we integrated bypass capacitors within the part itself, and that helped to reduce the noise even more by lowering parasitic impedances between the bypass capacitor and the actual silicon. And now we are at the third generation, and what we do here is, this is relatively new, what we do there is that we also reduce the low frequency noise between 10 hertz and 100 kilohertz, so that even within this low frequency band, the noise is extremely low.
Yeah.
And these switchboard power supplies then compete with ultra low noise linear regulators that customers had used before for such applications.
Yeah.
So that's the story behind the really lowest noise technologies within analog devices.
Okay. And I understand that there's, some nano power solutions for extending the run times of battery operated sensors. Can you provide some more details on how these solutions are designed and their impact on sensor longevity?
Yes. So this is a completely other area that helps to power the intelligent edge, which is really the lowest power or highest efficiency power conversion.
Yeah.
And some of these parts only have a power consumption while running, while providing an output voltage, a fixed output voltage of, let's say, 100 nanoamps, maybe 200 nanoamps, so really, really low quiescent current, so that the conversion efficiency is extremely high.
Yeah.
And then when you shut these parts down, because some of these intelligent edge sensors might only work for a minute, and then they might pause or rest for another minute, and then sense something again. Let's say we're sensing environment temperature. Typically, temperatures don't rise extremely fast.
No.
I mean, of course, in mass they can, in liquids or things.
Yeah.
But when it comes to just the environment, in some applications, it's okay to only measure once a minute. And and in the time in between, we tell also the power supply to stop working for a while, to rest, and by that save even more power. So this is another way. And then finally, one thing is, when you build a power supply that has to be extremely efficient at low power levels. Typically, power supplies sense the output voltage with a little resistive divider, and that resistive divider is also consuming current. It's consuming energy.
Yeah.
And so we've found ways to set the output voltage of such a power supply with only one resistor, so that during startup it sensed how much what resistor value hangs off of that part, and then during the normal mode operation, the part knows to set the output voltage to 3.3 volts or 1.8 volts or something like that, without the losses that typically a resistive divider brings to the equation.
Yeah.
So it's another little innovation that's within these parts, and optimization that you really do need when powering the intelligent edge, and at a low power level for some sensors that are remote, that aren't really attached to a power grid or to a SPOE, as we spoke about earlier.
And the concept of the silent switcher technology that you mentioned earlier was introduced to minimize radiated interference. So could you explain the process of how this technology was integrated into the power supply design and its benefits?
Yes. Well, first of all, it really is, we have to differentiate between radiated emissions and conducted emissions.
Okay.
Now, with the conducted emissions, it's always been possible to just add a filter to the board on the input side of the power supply or the output side of the power supply. While a filter, it consumes some space, it costs money, of course. It's still possible, and a great way to reduce the conducted emissions. But with the radiated emissions, there wasn't really a good choice, because with the radiated emissions, the only thing you could really do is put metal shielding around it.
Okay.
And metal shielding is just expensive and takes a lot of effort, and it's a nuisance within production and everything. The other way that existed was to make the switching transitions very slow, which helped with the radiated EMI also. But with really slow switching transitions, we have the problem that we have switching losses, very high switching losses, and then the efficiency would go down. So specifically what we changed is we introduced a symmetrical setup, as I said earlier, that would still cause magnetic fields, but these magnetic fields would have reverse polarity, and by that they would cancel each other out.
Okay.
And then we have changed the technology, how the die was attached to the lead frame within our products. So we didn't use bonding, or we're not using bonding wires anymore. And bonding wires add a lot of parasitic inductance, and that is causing then more voltage offsets, and these more voltage offsets would ultimately generate higher radiated EMI. And so these were, and then we of course have some secret sauce that we don't talk about, but maybe next time.
I'll hold you to that. Okay, following on from that then, can you tell us a bit more about your single inductor multiple output technology?
Yes, that's another technology that we have, let's say another innovation. So this is a way of generating multiple output voltage rails with only one inductor.
Yeah.
Because very often the inductor is the most expensive, but also the largest component within a power supply. And now, wouldn't it be nice if you needed to generate 3 or 4 different rails to only use one inductor rather than 4 inductors?
Yeah.
And this is helping us with the space constraint when the edge is transferred into the intelligent edge, where you need more electronics and more processing, and by that, to be able to live with the same kind of space that is available, we just need to use that trick with a single inductor, multiple output kind of technologies. And the way it works on a technical level is we charge the inductor with a certain bit of energy, and then we discharge this energy into one rail. And then we charge energy into the inductor again, and in that second step, dissipate that energy into the second rail, and so on. And by that, we can pretty much use one inductor in a time-stepped way for multiple output voltages.
Fantastic.
And that's a technology that's also relatively exciting. It's been around for a few years, but we keep releasing products for that technology.
So given the diverse requirements of the intelligent edge then, from higher power density to minimal noise.
Yes.
How do you foresee the future of power supply design evolving in this area?
Yeah. If only I had a crystal ball, of course. But I mean, it is foreseeable that the intelligent edge will even become more intelligent. And because what people are doing, they're putting artificial intelligence into the intelligent edge.
Of course,
so that's really the next step.
Yeah.
And that's clear. And so, of course, if you have artificial intelligence, typically you need even more power.
Yeah.
And if you need even more power, we have to keep doing what we're doing.
Yeah.
As in improving power supplies in all of these different aspects and angles to be even more efficient, to have even lower noise, right? And to be able to transmit even more power over one twisted pair line.
Yeah. Well, I think integrating AI is certainly inevitable, so it's going to happen.
It's going to happen.
Exactly. So more and more sensors are being used in industrial plants to help optimize processes and minimize downtime. And to keep up with this trend, it's going to be necessary to employ innovative technology like energy harvesting, which you've mentioned already. But can you share some more insights into the types of energy harvesting technologies that are going to be the most promising?
Yes. Well, I think there are about 4 main types of energy harvesting. So one of them is PV, photovoltaic, of course. It's a little solar cell. They're cheap, they work great, they offer a lot of power as soon as you have a good light condition, right?
Yeah.
So outside, they're perfect during the day. At night, they're not so perfect, of course, right? But that's one way. Another way is the TEG, the thermal electric generator harvesting. So that's if you have warm temperature, mass, and something colder, and putting such a TEG right in between it will generate power. But then you need to have something typically that's hot in your process within the manufacturing plant. Let's say you have like a steam pipe and a relatively cool air temperature around it, then such an energy harvesting type could work well.
Yep.
Another thing is the mechanical harvesting. So if you have vibration, you can just make a little magnet move through a coil, and by that generate peaks of voltages or bursts of voltages.
Yeah.
And you can harvest that. So it really, really depends on the exact application type or use case. And the last one, of course, is RF harvesting. So every radio signal has some energy, right?
Yeah.
But it's very, very little usually if you don't live right next to a cellular phone base station or anything like that.
Yeah.
So it's kind of hard to harvest that. But what we do is when you have a machine that has moving parts and you cannot put a power cable from one moving part to the other moving part, but yet we would like to do vibration sensing and put a vibration sensor there. We have to harvest.
Yeah.
But what we can do is we can generate an RF field, which is close by, with a transmitting antenna and a receiving antenna on the energy harvesting device, and by that harvest actual RF energy, and then have enough energy without pulling a cable or without this kind of thing. So these are the technologies behind energy harvesting. And again, we are working closely with the use cases to see what kind of products and solutions fit best.
Fantastic. Well, brilliant. Thank you very much for your insights. It's been a pleasure to have you back again. Before we wrap up then, is there anything else that you wanted to share with the community?
Yes,
I know there might be.
Yes, there's one thing. Since we are in Embedded World 2024 and we have a nice booth, the Analog Devices booth, I brought a really nice little module. It's a micro module. It's an LTP part. And what it really does is it can convert 54 volts or 48 volt rails down to 0.8 volts, which is extremely low, of course, in one step, and still have the efficiency above 90% while providing 200 amps of output current. So for a power management person such as I am, this is really innovative, really fascinating technology. That's why I just wanted to mention it. So if you're interested, just stop by the booth or check out our website.
Yeah.
Thank you so much for asking.
Thank you. And I'm sure I'll see you again next year.
Absolutely.
So thank you very
much.
Thanks, guys.